we continue with our discussion on simple harmonic motion. Recall from the previous lecture that we looked at the equation of motion for simple harmonic motion, and what we found is that if the displacement is x, then so let me call this displacement, then the equation of motion was d2x over dt square is equal to minus some constant x, and we identified this c which is greater than 0 as minus omega square x, where omega is the angular frequency. So, looking at this equation d2x by dt square is equal to minus omega square x, we also wrote the solution as x t is equal to some constant a cosine of omega t plus b sine of omega t, where constants a and b are determined by two conditions, which could be the displacement, for example, could be displacement and velocity at 0 or displacement at two different times, and we solved certain examples of this. We also learnt, besides the equation, so equation which was d2 x over dt square equals minus omega square x. Remember how we motivated this equation. This equation was motivated by looking at the x and y coordinates of a particle moving in a circle of radius r. It was moving uniformly with either speed v or angular speed omega, so that the angle it forms in time t is omega t, and its x component is given as x equals r cosine of omega t, and the y component is given as r sine of omega t, y t equals, and these are simple harmonic motions, right. And then through that we could get to the equation. We also learnt that this is a representation of SHM, and finally we saw in the last lecture that physically a spring mass system, when this spring follows Hooke's law, right, performs simple harmonic motion. So, this is a setup against which now in this lecture I am going to show you and discuss with you some more examples of where you see simple harmonic motion. So, these are the physical systems where simple harmonic motion takes place. One obvious question is, what happens if I take this spring and hang a mass to it in a vertical situation? Remember last time what we looked at was a spring and mass which was moving on, the mass was moving on a horizontal frictionless surface. Now I am going to look at a mass which is being hanging from a spring. So, what happens if the mass is m is that initially this spring is going to stretch and the mass is going to come down in some equilibrium position. How much does it stretch? Let us say it stretches by L, which is going to be mg by k, where k is the spring constant which we defined last time, m is the mass of the block and g is the gravitational acceleration. So, this mass comes down. What I am going to do next is pull it a bit by a distance y or push it up by a distance y and release. So, question we ask is, what happens if we pull or equivalently push the mass by a distance y and release it? So, let us see what will happen. As the mass is pulled down from its initial equilibrium position, which was at L, by a distance y, the net force due to the spring on it is going to be upwards, and this force due to the spring is going to be k. Net displacement now is L plus y. And of course, this force is pulling it up. So, I will just show it by an arrow up, and its own F due to m is going to be mg, which is going down. So, the net force is going to be k L plus y minus mg, and remember KL equals mg. KL equals mg, and therefore, all I am left with is ky pulling it up. Notice that the displacement is downwards, right, and the force is upwards. Therefore, I can write that when pulled down, the force on this is minus ky. On the other hand, suppose this spring is pushed up from the initial position where the mass was up to stretched from the length of the spring was up by L, and now I have pushed it up by y. Then the force due to the spring is going to be k L minus y, and it is going to be upwards because I am assuming that L is greater than y. So, the spring is still stretched, and F due to the mass is going to be mg and downwards. Therefore, the net force is going to be equal to again k L minus y minus mg minus ky, right, and this is minus sign. So, minus ky upwards or ky downwards. So, when y is up, the force is the other way, right. So, net force I can always write, therefore, whether the spring is pushed up or pushed down, F is always going to be equal to minus ky. So, the equation of motion is going to be m d2y over dt square equals minus ky, or d2y over dt square equals minus k over m y omega square still comes out to be k over m. So, even if you hang the spring vertically, right, it is being pulled down by constant force, the mass is being pulled down by constant force mg, even then omega square remains the same. A related problem could be that if I take this spring mass system, put it on a horizontal table and pull it by a constant force F. So, all that is going to happen is going to change is positioned to a new position, right, with this displacement being f over k. And after that, if I again displace it from that position, is going to have again the same frequency omega square equals k over m. So, the natural frequency of this system remains unchanged even when spring mass system is vertical or it is horizontal and still and being applied a constant force. All that happens is the equilibrium point shifts. Let us take the second example. Again, I am taking these examples to show you how different systems perform simple harmonic motion. So, in this system I am going to take a string pulled so that it has a tension T. I put a mass in between M, attach another spring, identical spring of length L of same tension T, and attach it on the other side to a wall. So, I have two strings of length L, both having tension T. They have been pulled up with this mass in between, and next what we do is displace. This was the initial position. Displace this whole thing a bit. Tension remains T. I will displacing it such that, suppose this distance is x, x over L is much less than 1. So, the change in the length of the string is not really much. Therefore, tension remains roughly the same. What is going to happen though is this mass is going to be pulled like this by the string on this side and like this by the string to this side. And therefore, there is going to be a net force F net in this direction on the string opposite to the displacement. On the other hand, if I pull this mass down like this is tension T, this is tension T, then the force is in this direction. So, you can see that when the mass is displaced, there is a force opposing that displacement. And how much is that force? Let us calculate that. Suppose this angle is theta. I can write in this side also theta. Then the net force on this is going to be one component of tension from right side, one component of tension from left side. Similarly, here these two components are going to give me the net force. So, F net is going to be that vertical component, which you can easily see is going to be T sine of theta plus T sine of theta, which is 2T sine of theta. Since x is much less than L, sine theta is roughly same as tan theta, is roughly same as theta is x over L, and therefore, F net is going to be 2T x over L, and in the direction opposite to the displacement. Therefore, I am going to put a minus sign in front. So, we have figured out that F net in this system is opposite to the displacement and it is minus 2T x by L. So, the equation of motion for the mass is going to be m x double dot is equal to minus 2T x over L, which I can write as minus 2T over L x, and therefore, x double dot is minus 2T over L m times x. Identifying this term as omega square, you have the mass now oscillating with angular frequency. Omega equals the square root of 2T over Lm, or time period is equal to 2 pi square root of Lm over 2T, and the general displacement yt or xt of this mass is going to be given as some constant A cosine of the square root of 2T over Lm t plus B sine of square root of 2t over lmt. So, that is another example just to show you that simple harmonic motion occurs almost every day in many different situations in our lives. Let me take a third example, example 3. Suppose I have a wooden block or any block of any material floating in some liquid, and let us call this block of uniform surface area A here, and it is floating in some liquid submerged by depth L. Here it is. So, it is submerged, this is a surface, and this depth from here to here is L. And from Archimedes' principle, I know that rho g L times A is the weight of the liquid displaced is going to be mg, where m is the mass of the block, all right. Rho is the density of liquid, L is the depth to which the block is submerged, G is the gravitational acceleration, and A I have shown you is this is A, area of cross section. So, I have A rho g L equals mg, g cancels. So, m equals A rho liquid times L. That is the mass of the block. Now, what we do is we displace it a bit. Suppose I push it down, all right. I push it down a bit, push it down by y. What happens? When I push the block down by y, so this is the liquid, earlier the block was up to depth L, and now we have pushed it down further by y. So, the lower surface is going to feel more pressure, and therefore, the net F buoyancy force is going to be the volume of the weight of the liquid displaced. So, area remains the same, L plus y rho g, and this force is up. The buoyancy force is always towards up, and F gravitation, force due to gravitation, is mg and is down, right. So, I can write this as minus, write this as plus, up sign as plus sign, and therefore, F net is going to be A L rho g minus mg is 0, right. We just found out that A equals A rho L, and therefore, A L rho g and mg are the same, they cancel, and you get the net force A y rho g up. So, if you are pushing it down, there is a force up, right. So, force is opposite to the displacement. Let us see what happens if I shift it up. So, suppose in the same liquid, right, the block was initially up to depth L, but now I have pushed it up by y, right. So, now the depth is going to be L minus y, and F buoyancy is going to be A rho g L minus y, it is still going to be up, and F gravitation of weight is going to be minus mg is down. Again, when I add the two forces, F net comes out to be A rho g L and mg cancel, and you get minus A rho g y up, and minus sign means down. So, this is going to be A g rho y down. So, when y is positive, that means it is being pushed up, the force is down. So, the net force, the expressions are the same, F net irrespective of whether the block goes up or comes down is minus A g rho y, is A g rho y, A g rho y. So, the equation of motion is going to be m d2y over dt square is equal to minus A g rho y, or d2y over dt square is equal to minus A g rho over m y. Remember, A rho times L was m. So, therefore, I can write this as g over L y. M over A rho is nothing but L, and therefore, omega square is going to be equal to g over L, or time period is going to be square root of L over g 2 pi, right. So, if it goes down by depth L, the time period is going to be 2 pi L over g. Next example I am going to take. Oh, by the way, before I take the next example, you can also generalize it to other shapes. So, for example, if I have this water and I submerge something else in it, right, that has a uniform cross section. So, for example, I could have a bottle that is submerged. In that case, when the bottle is pushed down or up, the relevant cross sectional area is going to be this cross sectional area A. Okay, so, you can work this out. I have given you already the idea how to work out these problems. Next example, number 4 I am going to take is a U tube of uniform cross section in which we have filled some liquid. And let us say this entire length of this liquid column is L. What we do now is push this liquid down, push it down so that in the new position the liquid is, let us say, goes up on one side, and comes down by the same amount on the other. So, this was the initial equilibrium position. So, it goes up by, say, amount y, and therefore, it comes down by an amount y. So, that the total height out here is 2y. It could be the other way also. The liquid could have been pushed up to the other side. By an amount y. This is y, this is also y. So, what happens now? This extra 2y height applies a pressure, extra pressure, and that pushes the liquid column down. As the height decreases, the pressure also goes down, and therefore, the force also goes down. Nonetheless, when the height is h, the force due to this pressure is going to be the cross sectional area A, the cross sectional area A times rho liquid times 2y times g, that is the net force. and is in the direction opposite to the displacement. So, if displacement to the liquid is higher on the left hand arm, then the force is pulling it down this way as shown here. The left arm it comes down, right arm it goes up. On the other hand, if the liquid is higher on the right arm, then the right arm it tends to go down and here it goes up. So, the force is opposite to the displacement. The mass of the liquid is the cross sectional area times L is the volume times rho liquid, that is the mass, and therefore, the equation of motion is m y d2y by dt square is equal to minus 2 a rho g times y. That is what we had calculated the force to be, 2 a rho y g, 2 a rho y g, and mass is a l rho. So, a l rho is equal to minus 2 a rho g y. A cancels, so does rho, and you have the equation of motion. Oh, there is a d2y by dt square. You have the equation of motion d2y over dt square is equal to minus 2g over L times y. This is exactly the same equation as that for simple harmonic motion, and therefore, you are going to have the frequency of simple harmonic motion given as 2g by L or time period of oscillations is equal to 2 pi square root of L over 2g. So, these are some examples that you see in daily life. You can do it even at home and measure this time and see that simple harmonic motion indeed takes place in this. I am now going to come to a very specific example of simple harmonic motion called the simple pendulum and derive the time period for oscillation of a simple pendulum. Whatever we do here, you can check at home also, because it is a very easy thing to make. All you do is take a string and tie a mass at the bottom. The extent of mass or the size of the mass should be much less than the length of the string, and then it becomes a simple pendulum. If you displace it to one side, the mass comes back, swings to the other side, the energy is not lost, to the same height and does a back and forth motion. So, first thing you notice is that the motion of the pendulum is periodic. But the question is the motion simple harmonic motion? And you will see, and it will become clearer if I may take this pendulum to be that made of a rod, that for large theta, if the displacement from the vertical is large, it is not simple harmonic. On the other hand, if theta is very small, then the motion is simple harmonic. So, let us see how does that happen. If the theta is small, then for small displacement, I can consider this to be almost moving horizontally, all right. So, that if the displacement is x, all right, the force in the x direction I need to calculate. Why is that force there? Let us analyze that. When the pendulum is displaced, and here I am going to make an angle, its weight mg can be written as two components. One component is along the string and the other one is perpendicular to the string, and it is in the direction opposite to the displacement. And this component, if this angle is theta, this component f perpendicular to string is equal to mg sine of theta. Okay, so here is the pendulum. It has been displaced by an angle theta. Here is weight mg. It has a component parallel to the string and the other component perpendicular to the string, and f perpendicular to string is mg sine of theta. So, force is mg sine theta, all right, which for theta much less than 1, okay, if the length of the pendulum is L and this displacement in the horizontal direction is x, then x or this arc length does not really matter for theta much less than 1. Therefore, this can be written as roughly mg theta, which is equal to mg x over L. And now I have to be careful and put a minus sign here, because the force is in the direction opposite to x, all right, and therefore, equation of motion m d2x over dt square is equal to minus mg over Lx. This is the equation of motion. I will cancel m from both sides and I get d2x over dt square is equal to minus g over Lx. This is the equation for simple harmonic motion. Notice that this is simple harmonic motion only under the approximation that theta is much less than L, or the displacement x is much less than L. Theta is much less than 1. So, what I have is for the pendulum, theta much less than L, or this x theta much less than 1, or x much less than L, I have d2x over dt square is equal to minus g over Lx, and therefore, omega square is g over L, or omega is the square root of g over L, and the time period t equal 2 pi square root of L over g. Notice that the time period does not depend on the mass of the bob or mass of that point, mass that you are hanging at the end of the string. It depends only on the length of the string. An interesting problem would be find the length of a pendulum that has time period of 1 second. We will go to the formula. 1 equals 2 pi square root of L over g gives you L equals g over 4 pi square, which I can roughly because g is roughly pi square, is 1 over 4 meters, or roughly 25 centimeters. And you see your wall clock at homes, the pendulum that swings there is roughly has the length of 25 centimeters, roughly, because I have taken g to be pi square. So, it will be very close to 25 centimeters, and that has a time period of 1 second. Next, what I am going to do is, so far we have looked at, so far we have looked at point masses performing SHM. Now, we are going to go generalize and see what happens if we deal with extended bodies, rigid bodies. and so on. So, as the first example, I am going to take a rod hanging with a pivot, pivoted at one end and hanging vertically, and when it is displaced from vertical, it starts going back and forth around the equilibrium position. So, it does perform periodic motion. Is it simple harmonic motion? That is the question we are asking. And let us see, it is very much similar to the simple pendulum that we discussed, but you have to be careful when you are dealing with rigid bodies. Remember, this whole body is one whole body, right. So, let me write, when dealing with extended rigid bodies, what is the equation that we use? We use torque equation. So, in this case, I am no longer going to use the force equals mx equation, but rather torque equals I alpha, where alpha is the angular acceleration equation. So, let us now formulate the problem and say a uniform rod of mass m and length L is pivoted at one end. So, let me make a picture. Here it is pivoted at one end. It is hanging vertically in equilibrium. If displaced by an angle theta from the vertical, write its equation of motion when it is released. So, what we are doing is we are displacing it by an angle theta and releasing it, and I want to write the equation of motion, number 1. Number 2, find if for theta much less than 1, it performs simple harmonic motion, and find its time period. So, let us see, this is a rigid body, it is a uniform rigid body, and therefore, the force acts at the center of mass at a distance L over 2. The force acts this way, mg, and it applies a torque. How much is the torque? Torque is going to be perpendicular distance, right. So, let me show it in different color. The perpendicular distance, which is shown in red, L by 2 sine of theta, and that pulls it back. So, the torque on the body is mg L by 2 sine of theta, and it is in the direction opposite to the displacement. An equation of motion therefore is going to be moment of inertia I of the rod times angular acceleration alpha is equal to minus mg L by 2 sine theta. Why this minus sign? Because the torque is acting in the direction opposite to the displacement. Recall that alpha is equal to d2 theta over dt square, and therefore, the equation of motion is I times d2 theta over dt square is equal to minus mgl over 2 sine of theta, or d2 theta over dt square is equal to minus mgl over 2I sine of theta. This is the equation of motion. Notice that on the right hand side I have sine of theta. Now, if theta is much less than 1, then I can write sine theta approximately equal to theta, and then the equation of motion becomes d2 theta over dt square is equal to minus mgl over 2I times theta. This equation is exactly the equation for simple harmonic motion. Recall that what we had written earlier was d2 x by dt square equals minus some constant times x. That x is replaced by theta now, except that there is no other difference. This is a constant, right? So, for small theta, theta much less than 1, this is going to perform a simple harmonic motion with omega square equals mg L over 2I, right. So, if I take a rod, uniform rod of length L, mass m, then displaced it performs simple harmonic motion with omega square being given as mgl over 2I, and for a uniform rod I is ml square over 3. So, omega square becomes mgl over 2 times ml square over 3, which is m cancels, 3g over 2l. This one of the l's also cancels, and the time period t is going to be equal to 2 pi over omega, which is 2 pi square root of 2l over 3g. So, this is slightly different, the time period is slightly different than that for a simple pendulum where all the mass was concentrated at the end. Another example of this is, suppose I have a disc and I pivot it at a point on its periphery. So, a disc, a uniform disc of mass m and radius r is pivoted at a point on its periphery, and now we displace it slightly with a small angle. By small angle theta. So, the question is, what is the frequency of its oscillations when it is displaced by a small angle theta from the vertical and released. So, what we are doing is we are taking this disc, displacing it slightly from the vertical position where it is in equilibrium and releasing it. We want to know the frequency. So, again here is the disc and it is been displaced slightly from its equilibrium position, and all the mass is acting at the center of mass, pulling it down, and that provides a counter torque to this, so that it is pulled back. How much is the counter torque? This is R, then the torque is going to be this perpendicular distance from the pivot and the vertical line passing through the pivot. Torque is going to be mg r times sine theta, and for a small theta this can be written as mg r theta, and therefore the equation of motion is going to be I alpha equals minus mgr theta, or I d2 theta over dt square is equal to minus mgr theta. By parallel axis theorem, I is going to be the moment of inertia about the center of mass, which is mr square by 2 plus mr square, which is 3 mr square by 2, and therefore the equation of motion is 3 mr square over 2 d2 theta over dt square is equal to minus mgr theta. Let us cancel m on both sides, let us cancel one of the r's on both sides, and therefore I get d2 theta over dt square is equal to minus 2g over 3r theta. So, omega square in this case is going to be 2g over 3r, and the time period t is going to be 2 pi square root of 3r over 2g. Another problem I am going to now do, just to show you how wide this concept of simple harmonic motion is something called the plasma oscillations. And if you recall from your 12th grade book, these occur, or you may have heard of plasma or plasma frequency while talking about radio waves in ionosphere. So, what a plasma is a collection of positive and negative charges, and when they are displaced with respect to each other, as I will show in the problem, they start oscillating together, and that is called the plasma oscillations, and the natural frequency for this is denoted by omega p, which is known as plasma frequency. So, the question that we are going to ask is problem. Shown below is a collection of positive and negative charges. We can say positive ions and electrons. Let me show this. So, this is like the positive charge shown by black, and on top of it is negative charge shown by red, and this is shown in slab geometry. The positive charges are fixed while negative charges are mobile. If the slab of negative charges is displaced as shown, it starts oscillating. Find the frequency of oscillations. So, what we are showing is that this negative charge is now going to be displaced slightly outside this. This is what is shown. So, that on this side there is negative charge, or what is left behind here on the back side is here is all positive charge. And then obviously this sets up an electric field which pulls the negative charge back. So, let me now explain the problem further. So, what we are doing is we have this slab on which we have this negative charges that have been displaced slightly. So, what is happening is here is this charge becomes negative, and what you are left behind with is this positive charge, and this sets up an electric field like this out here, and this electric field is going to pull this red thing back. So, there is a restoring force. Due to the electric field. If this restoring force is proportional to x or the displacement, then I know there is going to be simple harmonic oscillation. So, let this distance be x. Let the width of the slab be L. Let this area out here, area be A. Now, let us see if this charge has been displaced by x, how much is the surface charge out here? So, let n be equal to number density of the charges, all right. So, when I displace this by x, the volume that is out, this is shown here, which I am putting my pen over, which has been shown by purple and all that, is going to be A times x. So, number of charges is going to be n times A times x. So, charge, because it is a negative charge, is going to be minus n e a x, where E is the, let us say, electronic charge, if these things which are being moved are electrons. Exactly by the same amount, the charge on the other side is going to be, on this side is going to be n e a x. So, charge per unit area on both sides, which I will call sigma, is going to be n e a x divided by A, which is n e x. This is sigma. So, on the left hand side I have plus sigma, on right hand side I have minus sigma. So, electric field set up in between is going to be sigma over epsilon 0, which is n e x over epsilon 0, pointing to the right. And this is going to apply a force on these electrons. How much is the force? Force is going to be number of electrons n a l. We are assuming x is much less than L. N a l times the charge is E. I can put a minus sign, but since we are only calculating the magnitude, I can put a plus, times the electric field, which is n e divided by epsilon 0. So, this is going to be n square a l e square x divided by epsilon 0. And this force is going to be the mass of the electron which are going to move times the acceleration. Mass is going to be number of electrons a l times m e, mass of the electrons, x double dot is going to be minus n square a l e square x divided by epsilon 0. This minus sign shows that this is a restoring force. Now, I can cancel a from both sides, I can cancel n l from both sides, I can cancel one of the n's from both sides, and I am left with m e x double dot equals minus n e square x divided by epsilon 0. So, I am left with m e x double dot equals minus n e square x, x double dot equals n divided by epsilon 0, n e square over m e epsilon 0 times x, and this is nothing but omega plasma square. So, omega plasma square is n e square over m e epsilon 0, and this is known as the plasma frequency. So, this is a different application of the concept of simple harmonic motion to a collection of charged particles. As the final problem in this lecture, I am going to take a square of side A pivot it vertically at one of the corners and then displace it slightly from that position by an angle theta from the vertical position, and we want to know what will be the frequency of oscillation. Again, since it is an extended body, the equation that we are going to use is going to be I theta double dot, which is same as I, the angular acceleration, is equal to tau, the torque. The torque again, just like in the disk problem, is coming because of this weight mg. So, if we calculate it, this is the displaced square from the vertical. This is mg. Distance from the axis is the half the diagonal, which is a over root 2 sin theta. So, the torque is mg a over root 2 sin theta, and I put a minus sign in the front because it is in the direction opposite to the displacement, which in small angle approximation it becomes minus mg a over root 2 theta, if theta is small. And therefore, the equation of motion is I theta double dot is equal to minus mg a over root 2 theta, and omega square therefore is mg a over root 2 I. That is it. Now, we what got to do is substitute for I for the square. Now, I about the pivot is going to be I of Cm about the pivot plus I about Cm. So, I of Cm about the pivot is going to be m times a square by 2 plus I about the Cm, about this axis perpendicular to the paper, is going to be m a square by 6, which then becomes 2 m a square over 3, and therefore, omega square is nothing but m g a over square root of 2 times 2 m a square over 3. We can cancel m on both sides, one of the a's goes, and therefore, the answer you get is 3 g over 2 root 2 a. That is omega square, or the frequency omega itself is 3 g over 2 root 2 a raised to 1/2. So, to conclude, we have taken this equation d2y over dt square is equal to minus omega square y. You can have anything for y, it could be angle, it could be the displacement of water liquid or whatever, as long as the equation is in this form. This implies simple harmonic motion, and you can derive the equation of motion through consideration of the force and displacement in point masses or liquids being displaced. In rigid bodies, you can derive the same equation using the torque and angular acceleration equation, as long as the equation comes in the form where the acceleration is some proportional to minus the displacement. That constant gives you the frequency of simple harmonic motion, and the body performs simple harmonic motion.